Hi there everyone. In this video we're gonna continue on with chapter 2 and we're gonna look at the second part of two quantitative variables. This is called linear regression. This section and section 2.5 go together a lot. They have a lot of the same concepts, but we introduce a new idea here called linear regression. So let's jump right in. All right, you guys can read that. So we saw this scatter plot in the last video. This was the Florida house prices, and we saw that the correlation was 0.761, which is strong, positive. The graph shows us that it's linear, and the graph also shows us that there might be some outliers. So those are the four things we look for. What we do in this section is we use the scatter plot to make predictions. And that's something we really haven't done yet, right? But we can do it when you have two quantitative variables. You can actually use your data to make predictions. So if we were to draw a line on the graph that best represents the relationship between these variables, what would it look like? So just imagine a straight line that captures what all of the 100 data points are telling you. And it'll probably look something like this. So maybe the one you imagined was a little bit higher, maybe it was a little bit lower. So this is called a least squares regression line. Sometimes it's called a best fit line. It has lots of names. Don't be thrown off by the names. It's the only line we will use in chapter 2. So whether it says regression line or best fit, it's just a line that's drawn on a scatter plot. So the regression line is a model, and for our purposes, model just means equation. It's just a regular line on an XY graph like you see in algebra. And it tells us about the linear association between the variables. So let's use this regression line to estimate the average selling price of a 3,000 square foot house in Florida. So let me show you how you make predictions with a regression line. Without the line, you'd have to go over here to 3,000 square feet and go up and kind of guess, well, the price of the house is probably in this area somewhere. But when you have a regression line, so here's 3,000, all we have to do is go up to the line, and then you just go over, and whatever that value is, that is the average selling price for a house of this size based on the data that we're given, right? So the average selling price of a 3,000 square foot house in Florida is around $240,000. So I'm just estimating just from the way it looks, because I don't know the equation of the line at this point, right? We're going to use technology to find the equation of the line. But if you're given the line, you input the x value, go up to the line, and it outputs a y value, just like you saw in algebra with a linear function. So that's it. That's what we use this for. Once we have the equation of the line, we can get a lot more specific with these estimates. So if our data pairs are labeled x, y, the regression line is given by the equation y hat equals a plus bx. So again, this guy is called y hat. It looks like p hat. Remember in section 2.1 we had p hat. This is y hat. In statistics, whenever a letter has a hat on it, so that symbol is called a caret, C-A-R-E-T. Whenever it has a hat on it, that means estimate. Okay, so this is what we're using to estimate y. So if you go back and you look at this graph, it makes sense, right? We know the size of the house we're trying to estimate. So our y hat value, our predicted value or estimated value, is $240,000. None of these houses near 3,000 square feet cost exactly $240,000. But we're not trying to learn about each individual data point. We have the data set for that. We have the graph for that. This is a new thing where we're trying to make a prediction based on the data. So this number A, whatever this number happens to be, we're gonna do some more examples here in a sec. This is called the y-intercept, and B is the slope of the line. In statistics, we do not use y equals mx plus b. And what we saw last time, I'm going to switch over to the calculator here in a second. You don't need to do anything too fancy on the calculator, but I do want to show you something. So I'm just calling up my calculator app. I mean, I could use my actual calculator. It doesn't make any difference. They look pretty similar. I just had the phone handy. So I just want to show you, and we talked about this in the last video, that when you go to do these options, you're going to have, you can see number 4 and number 8. Remember, we use number 8. Lin Reg A plus BX. We do not use number 4, AX plus B. So if you're thinking y equals mx plus b, you might think number 4. We never use number 4. Look at number 8. A plus bx. That's what this is saying right here, a plus bx. You have to follow the form. Do not do y equals mx plus b under any circumstances. We are not computing the equations of these lines. Our technology is computing the equations. We are simply reading the equations, and we have to put these numbers in the right spot, right? Because technology is going to give us a and b, and we have to put them in the right place. So finding a regression line means finding values for the slope and intercept of the line that best describes the linear trend of the data. So the idea is that we could put this line anywhere, but it goes in a special spot on the graph that in important ways captures the information from all the data points. The details on that are not really important. We don't do any of this by hand. If you're interested in learning how to do this by hand, feel free to Google it, but don't say I didn't warn you. So the number by itself is the intercept. The number times x is the slope. You cannot switch these things. This is what I just told you about on the calculator. If you're having trouble remembering which one is x and which one is y, because that happens sometimes, you might be asked to put in a data set and you might forget which one is x and which one is y. That does happen. If it's easier to think about things in terms of the explanatory variable and the response variable, that might be easier. So if you just want to label the variables, right? So here we're talking about our Florida house price data set. The explanatory variable is the size of the house. The response variable is the price of the house. So if you can't remember which one is x and which one is y, just think a plus b times explanatory. So explanatory has an x in it. So there's a mnemonic for you, right? X explanatory. Got it? And the other one is response. So our Florida house price data set gave us this least squares regression line. So we don't calculate this thing, right? We use technology to calculate it. We have to interpret it. So we interpret it the same way you would interpret y equals mx plus b in an algebra class. The intercept is the value of the response variable. So if you just want to call it y hat, that's fine. So this is the value of y hat if the explanatory variable is 0. So our y-intercept here is 9,161. So that means if our house is 0 square feet, the price of the house is $9,161. Sometimes the y-intercept doesn't make sense in the real world. I'm not going to tell you what makes sense and what doesn't. You are also not required in this course to determine if a certain value makes sense or not. But I do want you to think about it. Because we just don't have time to spend all day on this, right? Let's hope this is a 35-minute video and you guys can get on with your lives. So think about it, right? If you have a 0 square foot house, so a non-existent house, can the price have any meaning? So think about this and we'll discuss it later. Sometimes it makes sense, sometimes it doesn't. Now, the number we're really interested in is the slope. So that's the number that's times x, right? Remember, x, explanatory. The size of the house explains its price. Even if it's not a cause a cause and effect relationship or a causal relationship, it's still an explanatory variable, right? It's easier to measure the size of the house than the price, right? So we use this to explain this, even if it's not cause and effect. So this slope is 7701. The way we interpret a slope is exactly the same way you interpret it in algebra. For every 1 unit increase in x, we get an increase of this in the price. And that's what it says down here, right? So the price of the home increases by $77.01 for every 1 square foot added to the house. This always makes sense. Slopes have to make sense based on the data, right? So if you're thinking about putting an addition on your house, you want to build a room like a 10 by 10 room and add it onto your house, you could expect the value of the house to go up about $7,700. That makes sense, right? So houses that are bigger do cost more money. So here is the fully general explanation of the slope and intercept. The slope B represents the predicted change in the response variable y given a 1 unit increase in the explanatory variable x. So this interpretation you basically have to memorize. You have some questions on the homework about this, but a lot of these are multiple choice. So you might be guessing. On a test, a slope question might not be multiple choice. Make sure you understand this concept, right? It just says if you move to the right on the graph 1 unit, then the slope is how far up the line will go. And the intercept is much easier to interpret. It's the predicted value of the response variable y if the explanatory variable is 0, right? So it's basically saying plug in a 0 for x, and a will be whatever y hat is. And again, I already stated what's at the bottom there, right? Sometimes it doesn't make sense for an explanatory variable to be 0, so the slope might not make, the intercept might not make sense. So make sure you're taking the time and thinking about this. Mostly in this section, I'm just using this one example. It does take some practice in a video like this because there are so many concepts to go over in this section. I really don't have time to do tons and tons of examples. Try the practice problems in the book, watch the videos in the ebook if you need more examples of this stuff. If you remember this from algebra, you're in good shape. It's the same thing from algebra. So here's how you make predictions with a regression equation. So if you're given the graph, you can just go up to the graph and then over. But if you're given the equation, you actually have to plug the numbers in. So let's use this equation to predict the price of these two houses. So let's say that you're a real estate agent, and you're trying to sell a 2,070 square foot house. You want to know, on average, what does a house like this cost? Well, you take this equation and you just plug in 2,070 into here. And then you take the equation, you plug in 3,110 into this equation. That's all shown on the next slide. So go ahead, type this exactly the way it looks into your calculator. Make sure you can get this answer. So if you want to pause the video while you're doing it, go ahead. I'm going to keep going. You also want to interpret this in words. Make sure that you are able to interpret all of these numerical quantities in words. Statistics is completely about word problems. So make sure that you're able to interpret. So the predicted price of a 2,070 square foot house in Florida is, and I just didn't even round it. I just left all the digits in there. If this is a homework problem, just follow the number of digits that the problem tells you. Right? So so the other one, we had a 3,110 square foot house. I can't talk today. Plug in 3,110. Pause the video if you're typing it on your own and want to double check. So again, when we say predicted price, that's what that hat means, right? Hat means estimate, predicted, and in some cases it can mean average, right? It just means what do we expect to happen, right? So this should not be a surprise at all, right? This house is a lot bigger than that house, so it costs a lot more. That totally makes sense. All right, so now we know how to plug in values of x to find values of y hat for different values of x. That leads us to some other ideas. So it's going to get a little theoretical here, just try to stay with it. This class, as we progress through the course, it gets more and more theoretical as it goes. So the predicted value is an estimate of the average response value for the given value of the explanatory variable, right? We just talked about that, right? That hat symbol means this is what we expect to happen. So if you have a 2,070 square foot house, you expect it to be a certain dollar amount. But we know that not every house that's 2,070 square feet costs exactly this much, right? This is an average, but the actual values of houses are certainly higher or lower, depending on the condition of the house, the neighborhood, number of bathrooms, does it have a yard, does it have a garage? There's lots of factors. So there's lots of variability for all houses of this size. This is the average or the predicted value, but we don't expect that to be the only value. So what we do is we look at a scatter plot and we can determine how far above or below each data value is from the value predicted by the regression line. So let's take a look at that. So that leads us to this definition called the residual. So the residual is the difference between the observed value and the predicted value. So what I have here is two houses. So here's a 2,070 square foot house right here. We predicted it would cost $168,000. In reality, it costs a lot less, as you can see. Over here, we have a 3,110 square foot house. And you can see that we predicted that it would cost about $248,000. But it certainly costs a lot more. So what you have to think about then is, if we're using these graphs to make predictions, we need to be able to determine, are the predictions good or bad? Are they accurate or not accurate? You can see for the vast majority of houses, this regression line would be a very good estimate. If we use this regression line to predict the prices of most of these houses, they're going to be very, very close. This house, not very close. This house, not very close. So what we do is we measure these residuals. And all you do to measure a residual is you take the actual value of the response variable and you subtract the predicted value. That gives you a distance. The residuals are allowed to be negative. Okay, so it's not really a distance. It's like a signed distance. So you get this formula, right? So the residual is just whatever we see, so whatever the actual cost of the house is minus the predicted value. And it reduces just y minus y hat. So that's just a little formula, little tiny formula. So we want to know, going back to this, we want to know, what are these residuals? So we need to look up in the data set the actual price of these houses and then subtract the predicted price. So all the points above the line have positive residuals. So again, let's go back and check this, right? Points below the line have negative residuals. Let's look at the graph and determine why this is true. This point is above the line. So why is its residual positive? Because its y value is bigger than its y hat value. Its y hat value is the line itself, right? It's the y coordinate of the line. So when we take this y value minus this one, we get a positive number. Down here, this one's below the line. When we take this number minus this number, we get a negative number because the predicted value is bigger. If the predicted values closely match the observed data values, the residuals will be small. So we just talked about that. Good predictions have small residuals. And there's one more fact about residuals. If we add up all the residuals from the regression line, the sum will always be 0. So that's kind of where this regression line comes from. You can imagine that this line could be anywhere on the graph. Just imagine it kind of moving around and rotating. But the spot that it's located is the place that the sum of the residuals is 0. And it has some other features too, but that's just a good way to remember it. So all the positive residuals cancel out all the negative residuals. It sits in the middle. So here are the actual prices of the two houses we just saw in the graph with the residuals. So then we're going to compute the residuals, and we're also going to compute which residual is farther from the regression line. So the way we do this, we've already computed y hat for both of these houses. So all we have to do is take y, so this is y, this is x. Remember, x is explanatory. We're using the size of the house to predict its price. Y hat is the predicted price, so we need to take y minus y hat. That gives us a residual. So remember, our residual is observed minus predicted. The observed value of that first house is $70,000, right? This was the predicted price from the earlier example. We already computed that. And we get a residual of negative $98,571.7. And again, you want to interpret it, right? The 2,070 square foot house costs $98,000 and change, less than what is predicted from the regression equation. So there's something going on with this house that causes it to be not a very good prediction at all. Perhaps this is an outlier. Maybe this house is in a really bad neighborhood, or maybe it's in Florida, maybe it got hit by a hurricane or something. So there's lots of reasons why houses can be above or below the line. If this is determined to be an outlier, then whoever is collecting the data would go back and look at it and decide whether to exclude it or keep it in the data set. Maybe there's a good reason for excluding it. But that's why we need to look at residuals to identify outliers. So here's part B. Now we have the larger house. It actually costs $338,000. In Florida, on average, its predicted price is this, which means this house is, the residual is $89,337.9. Again, pause the video at any time if you want to follow along on a calculator. I'm just doing addition and subtraction here, so nothing too fancy going on. So the 3,110 square foot house costs $89,000 and change, more than what is predicted. And that kind of makes sense, right? If you go back and look at the graph, right, let's go all the way back and look at the graph. Here's the really inexpensive house with this large negative residual. Here's the more expensive house with a large positive residual, right? So this is a positive number because this house is worth a lot more than what's predicted. This residual is negative because this house is worth a lot less than what is predicted. And that lines up with these answers, right? So which of these houses is farther from the regression line? Certainly this one, right? This one costs $98,000 less. This one costs $89,000, $89,000 more, but in absolute value, $98,000 is bigger than $89,000. So this one is farther from the regression line. What that tells us is that if there's exactly one outlier in this data set, it would have to be this one, not this one, because this residual is bigger. You don't have to find outliers. I'm just saying that if you were to do this in the real world, this is how it's done. Okay, now we're going to move into some cautions. So these are things that can go wrong with regression. Again, it's pretty theoretical. This is stuff you basically just have to memorize. We've done all the calculations that we're going to do in this section already. So, regression caution number 1, extrapolation. Extrapolation may not yield accurate results. So extrapolation is when a regression line is used to predict values outside of the range given by the data set. For example, we should not use our Florida house price data set to predict the price of houses less than 370 square feet or more than 4,050 square feet. So it turns out, if you go back and look at the graph from that data set, this is the smallest house included in the data set. This was the largest house included in the data set. So the predictions end at those values. In fact, let's scroll back and look at the graph. Right, here's our little tiny house of 3,070 square feet, and here's our giant house, 4,050 square feet. You can see that that red line stops at these, as soon as you see this value, stops and it stops. The line does not continue on. This line can only be used for predictions inside the range of values given. Anything on the outside is called extrapolation, and you can't do it. Well, I mean, you're allowed to do it. It just might not be accurate. All right, regression caution number 2, to always plot the data. We saw this in section 2.5 about always graph the data. Here, though, we're interested more in linear versus nonlinear. So it turns out that it's only appropriate to use a regression line when there's a linear trend. If there's a nonlinear fit, so there's lots of different ways for these things to be nonlinear, but we're really looking at the curved type of nonlinear. So this correlation is strong. So if somebody asked you what type of association is it, you'd say it's a strong negative association. But we can't use R to describe the association because the correlation R only describes linear association. Okay, so it's still negative, it's still strong, it's just we can't use the correlation as a measurement of that. You can see that if you use this graph to make predictions, these predictions are going to be all wrong. So if I try to make a prediction down here, all of these residuals are positive. If I try to make a prediction over here, all of these residuals are positive. And if I make a prediction in the middle, all the residuals are negative. Remember, for the residuals to be accurate, the values have to sort of randomly go above or below the line. Whenever you see a pattern like this where they're not jumping above and below the line, they're clustering up, that's always bad. Can't use regression in this situation. And last caution is about outliers. So we talked about outliers in section 2.5. It turns out that outliers also can influence the regression equation, not just the correlation. So what you would do so we already saw how to do residual outliers, even before we knew what residuals were, right? So we learned how to identify a point like this one as an outlier because it's above the trend given by the rest of the points. But there's another kind of outlier too. If you graph the x-coordinates, so remember how these are typed into your calculator, right? Here, let me show you. Oh, you know what? I'm going to do a calculator thing at the end of the video. I'll show you how you would do something like this. Anyway, if you have your x and y values, and if you just made a box plot of the x values, if you saw outliers in that box plot, the points that correspond to those outliers are called influential points. Because what those do is they rotate the regression line. What we were calling outliers before in the previous section move the regression line up or down. These influential points cause it to rotate, so the regression line can move around a lot based on these different kinds of outliers. In fact, I'm going to show you exactly how much movement can take place. So here, this is the data set we just saw here. So I'm just zooming in on this data set. I'm getting rid of this box plot. I'm just zooming in. And I looked at the most extreme outlier. So the residual outlier is what we called outliers in the previous section, even before we knew what residuals were. And then I looked at the most extreme influential point. This is also an influential point, but I just wanted to give one example of each to show you what happened. So let's say for some reason it is determined that one or both of these points does not belong in this data set. Maybe these are data entry errors, right? Maybe these are somebody like wrote down an extra 0 or something. So here's our R. So R is a strong positive correlation. It's linear. And here's B. B is the slope. Y equals A plus BX. This is our B. So this is the slope of our regression line, B. So what happens if we take out both of these separately? So on this graph, I removed the residual outlier. That's the one that was up here. The correlation jumped way up. The slope changed a little bit. You can see the slope came down. So removing the extreme residual outlier significantly changes both the correlation and the slope. So the correlation jumped up 0.26 and the slope dropped 29%. And you can see that this is a much more accurate representation, right? R went way up. So maybe there's a valid reason for removing that data point. What about over here? What if we remove this data point instead of this one? So that's the influential point, the one extreme influential point. Slightly changes the correlation because influential points aren't messing with the correlation too much. They change the slope. But notice removing the influential point, the slope increased by 31%. So it really took the slope up. So these, there's like 40 data points in these graphs. Just removing one of them, you can see it changes R and B a lot here and changes B a lot here. So the moral of this story, looking at outliers, is that you can't remove them just because you don't like the correlation. But if it's determined that these outliers are don't belong for whatever reason, then they should be removed. And we use graphs to detect them. All right, so now we're going to look at the technology side. This is actually the same thing we did last time. Oh, hold on a second. There it is. All right. So I just left everything up here. Oh, jeez. It went back to the beginning of the slideshow. Hold on a second. There's no way to go to reading view and have it stay on the same slide. Here we go, here we go. All right. So it's the same thing that we did last time. This is exactly the same slide as last time. Okay, but I want you guys to pause the video, try this on your own. Pause it here or pause it here, I don't care. Or just read the PowerPoints. And make sure you can get these numbers. So for the example that we're doing, it's the same data set as the one from the last example in section 2.5 about the bees dancing around. We already found the correlation, right? The correlation is here, 0.994. And I also explained in the 2.5 video how to type all this in. So go check that out if you don't know how to type this in. And I already did the stat key for this on a separate stat key video. So now we're going to do parts B and C, right? Find the equation for the regression line, round all values to the nearest integer. So here is our y equals A plus bx, even though it's y hat, so TI is wrong here. I don't know how anybody as bad at their jobs as these guys can consistently charge $150 for a product. This should say y hat equals A plus bx. So it's negative 399 plus 1174. So we're just going to round everything to the nearest whole number, and you end up with this right here. So if you want to write y hat negative 399 plus 1174x, that's fine. If you want to write it with the names of the variables like this, that's also fine. I don't mind either way, if you write it using y hat and x or the names of the variables. So all we're doing is just plugging in negative 399 here and 1174 here to get this. The calculator says y equals a plus bx, but it's y hat and this is x. Now part 3 says use this line to predict the time for, or the distance for a waggle dance of 1 second, right? So all you're going to do is just plug in 1 and just type it into your calculator exactly the way it looks, right? Negative 399 plus 1174 times 1. And make sure you can interpret it, right? The predicted distance, so distance hat means predicted, for a waggle dance of 1 second is 775 meters. Make sure you include the units as well. If a problem like this appears on an exam, you must include the units, and you have to follow the rounding rules properly. So here, for this homework, this is a homework problem, we're rounding to the nearest whole number. Follow the homework or follow the exam directions for rounding. All right, well, that's it. And we have one more video in chapter 2. And here's your extra practice. Try these book exercises if you need extra practice, or the video solutions and the video tutorials in the ebook. Both of those are really nice. So that's it for today. If you guys have any questions, you can post on the discussion forum, or you can email me. So until next time, study hard, and I'll see you later. Bye-bye.